Okay, new classroom, 3237, new class time 1 o'clock, and that begins on Monday. Also on Monday, if you look at the schedule for the semester, you'll notice that we have quiz 1. Now, I haven't decided yet what it's going to be on quiz 1, but I would like you to be prepared to solve potentially an HY8 problem, or a StormCAD problem, or it won't be 3 reservoirs. I will narrow that down because the 3 reservoirs assignment's not due until Wednesday, so I'm not going to quiz you on that Monday. But we have used Microsoft Excel for some other things, and so please bring your computer for the quiz on Monday. And that assignment that I was talking about earlier before we started the recording, that 3 reservoirs, there's 2 problems there, and it's due before class on Wednesday. And I have to go through and update in Blackboard all of the closing times. You know, previously you've had till 3 o'clock, so now it's going to be 1 o'clock. All right, so any questions on the announcements? All right. I probably have made this announcement to some of you already, but for the rest who haven't already heard it, the DOH is coming on Monday at 5 o'clock, and they've promised food. So even if you're not interested in an internship, you know, it's always good to at least listen to hear what they've got to say. You may end up at a contractor or a design firm that does work for the DOH, and so it's always good to see what kind of projects they've got going on, understand their policies a bit better, meet some of the people, and to eat some of their food. So that's starting at 5 o'clock. We confirmed, by the way, I think some of the announcements outside say 5:30, but it's 5 o'clock that they intend to begin. All right, today we're going to jump right to non-circular conduits, because a lot of the methods that we've used for determining pipe friction have D in the equation. For instance, if you think about the Darcy-Weisbach equation, H sub F is FL V² divided by D2G. So D means diameter, and not all pipes are circular. And so a square-shaped pipe isn't going to have a diameter. So it's just a small adjustment that we have to make to account for non-circular conduits, but that can be pretty important in some flow circumstances. You will recall hydraulic radius for a pipe that's flowing full is the diameter divided by 4. We can't make that same simplification if it's a non-circular pipe. And so the hydraulic radius we would actually calculate, instead of just having D divided by 4, for whatever the shape cross-section, we'd find what is the area of that section and what's the wetted perimeter of that section. So before we go any further, let's actually take a look at, for a square shape, just to make sure that we remember by the area, if we have some length and some width, the area would be the length times the width. Now the wetted perimeter is going to be the distance all the way around that's in contact with the water. And so it would be twice the length and twice the width. And so that's not going to, you know, if we have A divided by wetted perimeter, that's not going to simplify into anything. So you just have to calculate each term individually. Now, the substitution for the Darcy-Weisbach equation, instead of having the diameter in the denominator, we have 4 times the hydraulic radius. So you'd calculate the hydraulic radius for whatever shape you have, whether it's rectangular, square, maybe a pipe arch, and 4 times the hydraulic radius is the substitution in all of these formulas that normally would be using diameter. Reynolds number, for example, we've used Reynolds number to, you know, on the Moody diagram, or the Reynolds number goes into the Jane equation to calculate F. And so instead of the density, velocity times diameter divided by the viscosity, then it would be just 4 times the hydraulic radius. Or the one that I use more often than that version of the hydraulic radius, you've seen me say Reynolds number is V times D divided by kinematic viscosity. So if it's a non-circular conduit, then it's the velocity times 4 multiplied by the hydraulic radius divided by the kinematic viscosity. So it's just a simple substitution. Relative roughness, remember epsilon divided by diameter? Well, you'd probably guess it's going to be epsilon divided by 4 times the hydraulic radius. So that's on the Moody diagram, the right vertical axis is that relative roughness term. What about the Jane equation? You know, if we were going to use the Jane equation, I think I have that. If we go back a bit. Okay, here's the Jane equation. So you'd simply put the substitution for, instead of d, you'd have 4 times the hydraulic radius inside of the Jane equation, if you're going to be using that to calculate the F value for a non-circular conduit. Oh, okay, I've got it on the very next slide. Let's do that. Let's say that we have a box culvert, so it's square in shape, and it has a 12-meter length. We know that since it's concrete, that's going to have a relatively high equivalent sand roughness, so the K sub s or epsilon, the two terms are interchangeable. That's going to be what we use to calculate the friction factor F. So if it's flowing full, and we know the flow rate, which we can calculate V, remember velocity is Q divided by the cross-sectional area. So what's the head loss? How much H sub F is there for this 12-meter long section? And so the steps that you should follow, first of all, calculating the velocity. Then you can use that to determine the Reynolds number. Once you've got the Reynolds number and you've calculated the hydraulic radius, then you can calculate the F value. Once we have F, then you can calculate H sub F. So it's just to get some practice using this substitution of 4 times the hydraulic radius in place of the diameter.
What is that?
He was saying that when I give a demonstration with StormCAD, I should really emphasize how important it is to have accurate elevations for the catch basins.
Oh, that was a critique.
Yeah, kind
What did you
of.
say? You were like,
I haven't replied yet, but no, I'm happy to get the feedback. I think it's great. Yeah, because I guess it wasn't this class. It was the hydrology class where we were working with StormCAD.
Right.
So it's a Bentley product, and you guys have used WaterCAD, Water Gems. So he was watching a Bentley demo and saying, "Oh, you shouldn't just make up that value. You know, use the actual value." That's cool. I'm glad to have the feedback. Honestly, really. All right. So we've got water going through this culvert, and we want to know what the head loss is, but it's non-circular. So we'll come up with a cross-sectional area, determine the wetted perimeter. At some point, we're going to need to know the velocity. So we've done Q divided by A to get that. Here's our hydraulic radius, and since that's going to be a substitution for a lot of the things, including Reynolds number. So Reynolds number of 320,000, and that's going to go into the Jane equation. And so in the Jane equation, you'll notice we have the 320,000 here down here for the Reynolds number, and then a common mistake that I see a lot is people forgetting to put the K sub s and whatever length parameter in this side of the Jane equation into the same units. And so you wouldn't want to have 1.6 and then 0.312. You know, if you had it in units of meters, that would be a mistake. All right, but you do get the F value. It should be about 0.022. Anybody else get the same 0.022? A couple of people nodding their heads. And then substitute the F value, the length, the velocity, everything in, and it's going to be very, very little head loss through this culvert. But, you know, it's a short culvert. The flow velocity is relatively low, so there's not going to be a lot of head loss. In the homework assignment, I tell you to use a certain assumption to begin. And I want to tell you really quick while it's on my mind what that assumption is. Let me go to the regular Jane equation. Can I have it here? No, that's the revised version. All right, Jane equation. On the homework, you have to start off with an F value when you're doing the three reservoirs. Remember, in your first iteration, you don't know what the flow rates are yet. It's one of those cases where you have to begin with an assumption, and then you check the assumption and you make corrections and so on. If you don't know the flow velocity, you can't get the F value because flow velocity is required for the Reynolds number. Everybody with me so far? So you can't get the F until you know the V. That's the dilemma that we've always got. Well, one of the simplifications you can make is if the flow velocity is really high, so if you've got a big V, what is that going to do to the Reynolds number?
It's going to make it small.
A big
Reynolds
V,
number?
a big V means a Reynolds number is big, but since it's in the denominator, that makes this term small. So the fully turbulent flow assumption is if you have a big Reynolds number, like if the water's moving really fast through the pipe, then this term doesn't matter because that makes the Reynolds number so big that the F value is only based on the relative roughness term. So there's these two factors that determine the friction factor. There's the first term, which is the relative roughness, and the second term is related to the flow velocity. So the fully turbulent flow assumption that I talk about in the homework assignment, the fully turbulent flow assumption is assume we've got a really big velocity, so that first iteration you can get a guess for the F value just by having the Jane equation would be F is 1.325 divided by the logarithm of K sub S divided by 3.7D. And that's, well, that last quantity squared. So that is when you assume fully turbulent flow. So for that iteration 1, you assume fully turbulent flow and you calculate the F that way. Iteration 2, you don't assume that anymore. So for iteration 2, you go back to the full Jane equation because now you know the velocity, and if it's high, it'll take care of itself. It will become insignificant in the equation, but it's just a way of eliminating it from being an implicit equation in that first iteration. Does everybody understand? Any questions about that? Okay. The other thing we're going to be talking about today, besides non-circular conduits, is local losses. And we talked about this in fluid mechanics briefly. And in fact, we even characterized some of the local losses. For instance, if you have a small diameter pipe that has a junction and feeds into a large diameter pipe, you can calculate the localized reduction in energy at that spot by having the difference in velocities squared divided by 2g, and there may be a calibration curve that a calibration factor that you also apply depending on if the transition is abrupt or if it's tapered and gradual. So the general form of local losses is that we have a K value that we apply by the velocity at whatever the junction is. And so if it's a change in direction, there would be a K value that we can oftentimes look up out of a table. These are sometimes called minor losses because in comparison to pipe friction, local losses usually aren't significant. But if you have a lot of fittings in a system, then they can add up. So here's a table that is in your textbook, and it's showing a variety of different relative diameters. So for example, if you have a big pipe going to a smaller pipe, how different they are in size is going to affect what K value is used. And so each of these factors here would be the K value that's applied before the velocity head. So that's one term, is how different are the pipe size diameter. The other is how gradual the transition is, and so the taper angle that's connecting the two pipes. And so 180 degrees would be just an instantaneous connection, meaning that your large pipe immediately transitions down to a small pipe with a rectangular angle between. So there's going to be a lot more turbulence and therefore a greater amount of energy loss in a case like that than in comparison to a taper angle of 60 degrees. And so you'll notice that here the K values are much lower than they are for the flat transition. A similar effect is true for the expansions. The K values are larger for a more dramatic 180 degree transition. There's in your table in the textbook a variety of different valves. We'll look at a cross section at some of those valves to see why, for example, why does a globe valve have such a high K value even when the valve is all the way open. So a K value of 10 is pretty significant. What that means is that 10 times the velocity head is being lost in energy as the water goes through that transition. So let's jump ahead to the valves and do the comparison between a globe valve and a gate valve. And so you'll notice in this gate valve, the water is flowing down through a pipe, and if the gate is in place, then obviously the water's not going to be able to go through it. But if the gate is out of the way, then it's essentially just, it's not changing direction. The water continues in the same direction that it always was. There might be a little bit of turbulence here at the edge, but in contrast to the gate valve, the globe valve has a really dramatic change in direction it has to go through. The water is entering the globe valve, and then this plug is pulled up out of the way when the globe valve is open. So if you open up the globe valve and the water is having to flow through, then it's changing directions 180 degrees, well, I guess 90 degrees once, 90 degrees a second time before it flows back out. And so that's why the K value, even for a large diameter globe valve that's all the way open, is going to be 10 in comparison to a loss coefficient of 0.15 for a gate valve.
Would that make it difficult to, I guess, manually operate those? Or are they, is there a way to get around that? Like if there's a lot of pressure to get around that, or a lot of force to get around that?
Good question. Yeah, that's a good question, like the operational considerations. As far as the operational considerations, I'll mention that a globe valve, if you have a high pressure environment, a globe valve is going to be better to prevent leakage than a gate valve is. And that's because there can be a rubber O-ring that goes around the opening here, and this globe can go down and kind of seal against it with quite a lot of force, and it's harder to have that same seal with a gate valve. And so you may be asking, well, why would anyone ever bother with a globe valve if you have so much energy loss through it? And it's largely because it's able to hold back a higher pressure than a gate valve is. And as far as the ease of opening, if there is a high pressure, then that could be pushing the closed gate up against the frame that it's setting in. But I think probably like what would make it harder to open and close is more often just going to be like corrosion and rust and like friction in the handle and the rotating assembly in the threads, rather than the hydrostatic forces that are pushing on the gate.
Oh, okay.
But the main concern with the globe valve is just that it has a really efficient seal. A check valve only allows one directional flow, and it's becoming increasingly common for people to put a check valve, for example, the water that leaves their house going towards the sewer, you'd put a check valve, a one-way flow valve, so that if there's a really rainy day and the combined sewer is beginning to fill up with rainwater, then the wastewater wouldn't back up towards your home. It would just force itself closed. And even when the check valve is all the way open, a swing type check valve is going to have a K value of 2.5. There's other types of check valves, like where a ball is inside, and kind of the flowing water lifts the ball up out of the way, and then the water going the opposite direction would kind of have it clog a hole. But because the water, you just have to think about how much of the flow path is obstructed. It's partly about the direction change, but also look at the diameter that the water is flowing through. In the case of this gate valve, the diameter of the opening when it's full is the same as the diameter of the pipe. But in this globe valve, not only is it changing direction a lot, but all of the flow is going through this tiny little diameter here between this bottom edge and the top edge. And so the diameter of that opening is going to be smaller than the diameter of the pipe that's feeding the globe valve. And so these other specialty type valves like check valves, the ball opening, the ball that's inside of the valve is going to be taking up a lot of the flow area, and so the water's having to squeeze through a smaller space. These coefficients have to do with water that's leading out of a reservoir or a tank. And so if water is going out of a reservoir through a pipe that's flush up against the wall, then you'd use a K value of 0.5. But if the pipe extends into the reservoir, the K value is 1. With tapering and the right radius of curvature, you can get the K value to be as low as 0.04, just because there's less of induction losses as the water is beginning to enter the pipe, and a reduced amount of turbulence. But the angle that the pipe leaves can also contribute to the K value. And so here they're showing that if it was departing at an angle, not only are you having the water losing some energy as the flow is entering this pipe, but also it's changing directions. And so it's having to converge onto a small opening and then change directions as soon as it gets to that opening. So you'd have some additional losses having to do with the angle itself. This is a cutaway that kind of shows another aspect of why you have such high losses in a globe valve, because of the change in direction and then this small opening that the flow is passing through. In the case of a ball valve, the flow diameter isn't decreased when the valve is open, and the advantage of a ball valve is that it can be closed very quickly. You remember down in the hydraulics lab, the pipe rack, those yellow handles that you can just immediately take it from horizontal to vertical, and then the pipe stops. Those were ball valves, where all it takes is, I guess it would be a quarter turn, and the flow is shut off completely. All right, let's combine the idea of local losses with another practice problem having to use the Hazen-Williams equation. So the Hazen-Williams equation is characterizing our friction losses. We're going to keep track of the local losses here and assume that we have water going through both a pipe bend, a globe valve, another pipe bend, and we're trying to find out downstream a distance of 1 kilometer what's going to be the pressure at some location where we know the pressure at A. So here in the energy equation, sometimes we get sloppy and write H sub F as the final term in the energy equation, but technically the losses include both the friction losses and the local losses. So this time we're going to be precise and keep track of the effect of both of those in order to predict what's the pressure downstream. So water is flowing from A towards B, and so location A is 1, and location B in this equation will be 2. Note the problem statement also says there's an elevation difference.
It does make a difference.
Okay, so our friction losses using Hazen-Williams is about 43 meters of head. The local losses is about 8 meters of head. And then we rearrange the energy equation to solve for the unknown pressure at 2. And so if you think about, like, what is going to be the pressure at location 2? It's going to be related to the pressure that there was at 1. So this is how much you've got to start with. And so the pressure is going to be lower downstream because, number one, the elevation is higher. So since it's elevated downstream, that's going to reduce the pressure. So you'll notice the minus sign there is because it's higher downstream. And we're going to have less pressure at 2 because of the effect of the pipe friction. So the minus there means that we're reducing the amount of pressure that we'll see downstream, and also the local losses. And so there's only about 2 meters of pressure head downstream, which gives us 21.3 kilopascals downstream. And that's not enough. The minimum during an emergency, most municipalities insist on at least 140 kilopascals to prevent contamination of the pipes. And a more typical operating range for a municipal water system would be starting at a low of 240 kilopascals. And so under these conditions, like if this was an actual design, what we'd say is probably that pipe is too small. You know, if you've got so much water going through the pipe that it's flowing at 4 meters per second, and you're going from a pressure of 650 kilopascals all the way down to 20 kilopascals, this pipe is probably undersized. So, but that gives you some example practice accounting for the local losses, and it's always good to get practice with Hayes and Williams. Any questions on this one? All right. I'm sorry I misspoke earlier when I was giving you the announcements. So the quiz, we are having a quiz. We're having a quiz on Monday. It'll be in our new classroom at our new time, but it won't include HY8, it won't include StormCAD, it won't include water gems, but you might need to use Excel. So do bring your laptop for that. I'd like to think I wouldn't have given you the wrong quiz. I may have said it, but I'd like to think if I actually prepared it and it had an HY8 that it would have occurred to me before I handed it out. But still, I'm glad that you caught me now. Now we won't have to know the awful truth.